This vector addition review, although not part of the AC analysis in the foregoing topics, but the understanding of this elementary concept can help us grasp the idea of sinusoidal wave addition later on, especially in a graph representation. To review graphically, you simply place all the vectors at the tails. So I have these vectors A, B, and C. And if I use the head to tail method, I can take vector B and move it so that its tail sits on the head of vector A. And now I can move vector C and place it at the tail of vector B. And the resultant connects the beginning or the tail of vector A to the head of vector C, and there was a beginning to the end, and you have it right there. So if we were to solve this graphically, you would see the resultant is the purple vector located as shown. To find the resultant algebraically, we need to first find the x and y components of each vector. So the x component of vector A is right here, and the y component of vector A is over here. And likewise, the x component of vector B is located here, y component over here. Notice that there is no y component for vector C. Vector C lies entirely on the negative x-axis, so that this is the value we'll be using when it comes to use it. Let's take a closer look at what we actually do with all these components. We'll be adding up all the vectors on the x-coordinate and also adding up all the vectors that are on the y-coordinate. And we'll use these vectors to determine the resultant. So this makes us look a little bit easier. Let me take away the original vector A and vector B, and we're just gonna work with the components. So we're gonna find the sum of all the vectors in the x direction. So that would be the x component of vector A and the x component of vector B. Remember, this would be done head to tail. And then vector C lies entirely on the x-axis, and that's in the negative direction, so we have to subtract that. And so the sum of these three vectors is going to be just this distance and direction here, indicated by the purple arrow. Now let's add up all the vectors acting in the y direction. Let's take the y component of vector A and the y component of vector B is negative, so that has to be subtracted. So let's go ahead and show that being subtracted. So the sum of these two vectors then is this little vector here as shown. These two vectors are the legs of a right triangle that define the resultant. Let me show you. Let me take the sum of all the x's and put it back on the x-axis. Let me take the sum of the y's and put it momentarily on the y-axis. But to show that it forms a right triangle, I'm gonna go ahead and make it head to tail. Just move it over here at the end of the x-axis. And so our resultant is actually this vector right here. And now you can use the Pythagorean Theorem to find the actual value, the magnitude of that vector, and then we'll be using the tangent function to find its precise direction. I gotta go back to the previous slide. As you can see that we get the same resultant using either method. I did it graphically here using the head to tail method, and I actually did it graphically on this page using the sum of the vectors in the x direction, the x components, and the sum of the y components to find the resultant. Let's go ahead and use actual numbers now. Here's the coordinate plane, and I like to set this up using a tabular format where I list the vectors A, B, C across the top, and then when I go across, adding all the vectors that are acting in the x and y direction. Now these are the vector components that I showed you on the previous slide. So let's get the values now, and you see the x component of vector A is 80 cosine 65. You can see the vector flashing as well as the value. The x component of vector B is 100 cosine 20. And the x component of vector C is vector C. And that is a negative value, so that is subtracted. Now if you're not comfortable with the trigonometry, we can come up with these values as I have right across the top. Don't get stressed out. I'll show you on the next page where you can calculate these values out to the side and then plug them into this table, and it will look just like this row here where I've done the calculations. Sum of the x components is equal to 33.8 plus 94 minus 60. That gives us a value of 67.8. We'll do the same thing to the y components now. The y component of vector A is 80 sine 65. The y component of vector B is in negative direction, so that has to be subtracted. So it's a negative of 100 sine 20. Vector C does not have a y component at all, so that is 0. We put these values in the calculator and we come up with 72.5 plus negative 34.2 plus 0 is 38.3. As you can see what it looks like down here. So the sum of the x components, 67.8, can be represented by the vector here. And the value for the sum of the y components can be represented by this vector, purple one here. And this should look familiar as we already had this drawn on the previous slide. I'm gonna pick this up, the y's, sum of the y's, and you can see our y component. That's our two legs of the right triangle. So we can then define the resultant by using the Pythagorean Theorem. We'll take the square root of our sum of the x squared plus the sum of the y squared, and we get a value of 77.9 for the resultant. And we click on it and we can see that value with the vector looks like and what the value is. To find the direction, we have to use the tangent function. Let me pull this out. So the tangent of the angle, and we're talking about the angle between the x-axis and the resultant. The tangent of that angle is equal to opposite over adjacent. We can see that the opposite side is our value for the sum of the y components. That is 38.3. The adjacent side is our value for the sum of the x components, 67.8. We take the inverse tan of that ratio, 38.3 divided by 67.8, and we get a value of 29.5 degrees. Your answer then would be that the resultant is equal to 77.9 at 29.5 degrees north of east, or you might say 29.5 degrees above the positive x-axis. Remember, vectors include magnitude and direction.
Okay, time for my face to show up. Anyway, that was just a review of the graphical and analytical solutions of vector operations. Now, it's time to tackle with the real deal. First of all, we should start at the very basic, which is the sum of two alternating n-phase waves. In order to understand the concept, it is shown here graphically I1 and I2. When they are combined together, they will yield a resultant wave, which is represented right here as IT, the magnitude of which is just the sum or the arithmetical sum of the magnitudes of I1 and I2. The phasor diagram on the right is just another representation of these three waves. It is clearly shown right here that the length or the magnitude of IT is just equal to the length of I1 and I2 combined. Algebraically, it is represented as IT is equal to I1 plus I2. Or put it in another way, IT is equal to I1 with 0 degree phase shift plus I2 with 0 degree phase shift, which means that I1 and I2 are in phase with each other. This time, let's take a look what will happen if we combine two waves who are out of phase by each other by 90 degrees. Right here, we have I1 and I2, where I2 lags I1 by 90 degrees. When we combine them together, they will yield another sine wave, the resultant wave, IT. The magnitude of IT will always be greater than the magnitude of either I1 or I2. In the phasor diagram, it is fairly easy to see that I1 and I2 forms a right triangle when we project I2 right here. So, when we want to find IT given the I1 and I2, we will just recall the Pythagorean formula. With the help of the graph that forms a right triangle, we now construct the formula for the resultant wave. IT is equal to the square root of the sum of I1 squared and I2 squared. Or put it in another way, IT is equal to I1 with phase shift of 0 degrees plus I2 with phase shift of negative 90 degrees. This means that I2 lags I1 by 90 degrees. Another scenario that we will cover is when the two sinusoids or alternating waves are out of phase with each other by an acute angle theta. Here we have I1 and I2. I2 lags I1 by a certain acute angle theta. When we combine them together, they will yield another sinusoids, IT, the resultant wave. In order to comprehend what happened here, let's take a look at this phasor representation of the two waves. I1 being our reference sinusoids lies in the 0 angle position, and I2, since it lagged I1 by an acute angle theta, is located right here. Now it's time to apply our knowledge of the vector operation graphically in this situation. The parallelogram method can be applied here. So let's make a parallelogram by sliding I2 over here and I1 at the bottom. Now let's do that. think it's a bit diagonal. So that was a perfect diagonal. Okay, the parallelogram is already completed. Now it's time to draw a straight line here. What we have done is the IT. Now we found the resultant graphically. Now it's time to find the resultant analytically, or in other words, algebraically. So we'll derive the formula out of this graph. As you can see, right here, it's just the same angle here. So we name this as theta since they're equal. This straight line forms 180-degree angle. So inside of this is 180 minus theta, right? So let us now focus on this triangle right there. Erase this one in your mind. Now we have formed a triangle, an obtuse triangle. Okay, that's an almost perfect triangle. This has an angle of 180 minus theta, and this is I1. Well, this one is I2. Remember the cosine law? When these two sides are given, I1 and I2, and the angle between them, we can find this side using the cosine law. Cosine law states that if we have a triangle with sides A, B, and C, and an angle gamma between A and B, the length of C is given by C is equal to the square root of A squared plus B squared minus 2AB cosine gamma. So similarly, when this is replaced by I1 and I2, and this will become IT, and this one will become 180 minus theta. Let's put that over here. I1, I2, IT, and 180 minus theta. The formula will now become IT is equal to the square root of I1, I2, I1, I2 and this angle right here will become 180 minus theta. And here you go. There we find the analytical solution of the resultant IT. In order to emphasize, I rewrite the formula for the resultant wave of the two sinusoids who are out of phase by an acute angle, and together with its complex number format in the bottom. The complex number format is IT is equal to I1 angle 0 degrees plus I2 angle negative theta degrees. I will show you later how to use this to have a quick calculation with your calculator. Test our understanding of the concept by a couple of problems. The first problem is the current in a given conductor is represented by the geometric sum of two currents whose equations are I1 equals 15 sine omega t and I2 is equal to 25 cosine omega t. The problem asks for the RMS value of the current in the conductor. And now let's list the given here. I1 equals 15 sine omega t and I2 equals 25 cosine omega t. Sine omega t. This is I1 and I2 is equal to 25 cosine omega t. In our trigonometry, it is equal to 25 cosine, no, sorry, 25 sine omega t plus 90. By inspection, the currents are out of phase by 90 degrees. So our formula will be of that of the Pythagorean Theorem. IT is equal to the square root of I1 squared plus I2 squared. Let's plug in the values. Is equal to 25. Now the 15 must be the first because it's the I1. 15 squared plus 25 squared. Is equal to, let me take my calculator. Okay, square root the square root of 15 squared plus 25 squared is equal to 5 squared over 4, or 25, or 29.15. So the answer is 29.15. Or if you want to be fancy, let us use the complex number format. That was IT is equal to I1 plus I2 is equal to 15 angle 0 degrees plus 25 angle 90 degrees. How do we do that? Okay, here we go with the calculator. First, change the mode to complex mode, then to complex 2. Now as you can see, there's a complex word at the upper corner of the calculator. Now make sure that the complex must give the answer in polar form. Shift, set up 3, 2. Dapat sa arteta siya. 2. So let's plug in the values. 15 shift angle 0 plus 25 shift angle 90 equal to that's the answer. 29.15 angle 59.04 degrees. It's equal to 29.15 angle 59.04 degrees. These answers are both correct. Okay, another problem to practice on. You can get your calculator if you want. So we have here get the sum of the voltages as given. V1 is equal to 25 sine omega t, and V2 equals to 35 sine omega t plus 60. As you can see, the phase shift is an acute angle. So you already know that if it is an acute angle, we will use the cosine law. So here we go. Get your calculator and solve ahead of me. E1 E sub t is equal to the square root of E1 squared plus E2 squared minus 2 E1 E2 cosine 180 minus theta all over square root all over them. Plug in the values. E sub t is equal to the square root of v sub 1 is 25 squared plus 35 squared minus 2 times 25 times 35 cosine the phase shift is 60, so 180 minus 60 with a square root all over them. Check your answer. The answer is equal to, I've already calculated this, so it's so easy for me to put this 52.2, of course the units, volts. Okay, now it's time to use the complex number format. E sub t is equal to E sub 1 plus E sub 2, 25 0 degrees plus 35 angle 60 degrees. The answer should be 52.2 angle 35.5 volts. Okay. This answer and this number format, complex number format answer are both correct. If you didn't get the answer, then your calculator is not working well, or maybe the one using it is not working well. Joke of the night. Okay, let's have a summary of what we have learned today. First of all, we have reviewed the graphical and analytical vector operation. And after that, we've found out what is the sum of n-phase sinusoidal waves, and also the sum of 90 degrees out of phase sinusoidal waves. And the last that we have tackled is the sum of acute angle, which is represented by theta, out of phase sinusoidal wave. And at the end of the discussion, we have answered a couple of problems that illustrate the concept of what we have learned.